All right, so here we're starting with lesson two. Lesson two has to do with functions. We're going to take a look at what a function is and the difference between a relation and a function. So a relation is a set of ordered pairs, an input or output. The domain of a relation is the set of all the input values, and the range of the relation is the set of all the output values. So we have the domain, which is our inputs, and the range, which is our outputs. A function is a relation that assigns a unique range value for every domain value, with ordered pairs in the form x, y. The x values are the domain, and the y values are the range. So the notation y equals f of x is called function notation, and it is used to describe functions. For example, in the function f of x equals 4x plus 1, f is the function, x is an element of the domain of f, and f of x is the output or the range of f corresponding to the input x. So there's a lot of heavy things in here, but when we're going through here, if we take a look and see where it says y is equal to f of x, that's something to remember as you're thinking about these functions here. So when we have f of x written like that, when we're looking at it, we'll also might be a little bit more familiar with y equals 4x plus 1, right? So this is another way to write our function that we have here. It's just not in function notation because it doesn't have the f of x, but it still shows that we have the inputs for our x values and the outputs for our y values. Now, one important thing about a function is that it says that there is a unique range value for every domain value. And what that means is that when we have some x values, each x value can only go to one range value. So each x only goes to one y. Now, more than one x, right, can go to the same y, but there cannot be two y's that come from one x here. And we'll take a look at that a little bit later on. All right, so it says you can determine if a relation is a function using any of these methods. So the first way we can check is that no domain values are repeated. Another one is by looking at a graph of the relation. And the third is using a mapping diagram. So if we take a look, the first thing we're going to take a look at is the vertical line test. So a vertical line, right, remember, is a line that goes straight up and down and is parallel to our y-axis. So a vertical line test can be used on a graph to determine if a relation is a function. If a vertical line passes through no more than one point at a time, the relation is a function. So for example, look at the two graphs below. So this graph here is a function since each vertical line drawn passes through only one point, and each domain value x has only one range value y. So this was a function, right, that was made up of these points here. I'm kind of filling in. And when we draw a vertical line, there is no vertical line that can go through more than one point at the same time. Right? So there's no straight up and down line that we can draw that can go through any of these points at the same time. However, if we take a look at the second function, or the second relation, right, which is made up of these points here, if you notice this line that they drew at x equals to -3, right, has two y values that it hits. So this does not pass the vertical line test because it hits 2 points in this relation. So this would not be a function. While our first diagram here passed the vertical line test, so it is a function. All right, so if we take a look on the next page here, some relations are graphed as a set of continuous points that form a straight or curved line or part of a line. So for example, in the graph below, the data is continuous at all values of x from -5 to 5, except at where x equals 3. And there's a break in the graph. So if we take a look, right, this graph continues through here, up, over, then there's a break, and we notice that with an open circle there. And then it starts again up here at 3, 1, and continues straight. all the way up to 5. So notice the open circle at 3, -2, so right here, and the closed circle at 3, 1. The open circle means the point 3, -2 is not part of the graph, but the closed circle means that 3, 1 is part of the graph. Having one open and one closed circle at points where x is equal to 3 means the x value corresponds to only one y value. Therefore, this relation is a function. And the vertical line test can be used to show this. So if we were to draw a vertical line, there is nowhere on this graph that we can draw a vertical line that will hit more than one point, including here at x is equal to 3. And the reason for that is when it hits this open circle, there's not a value there. The only time that x is equal to 3 has a value is up here at 3, 1. So if we take a look below, the sample question here says, which statement best describes the relation graphed below? So if we take a look here, we have a relation, and then a relation is a function if it passes the vertical line test. So if we're looking here, so from 0 to 2, right, it passes our vertical line test, because even though there's two open circles here, that just shows that there's a gap in the domain. It does not show that it is not a function. However, when we look here, when x is equal to 4, this function does not pass the vertical line test because when x is 4, we have two values for y. So if we're looking at our domain, right, our x values and our range, our y values or our f of x values, at 4, this 4 matches with both 3 on the y-axis and 4 on the y-axis. So because there are two y values, or two f of x values for one of the domain values, it is not a function. So if we're looking at our answers down here, we automatically can cross off the ones that say it is a function. So it is not a function. And then if we take a look here, the relation is not a function since the x value 4 corresponds to more than one y value, which is our correct answer here, right? Because the y values can correspond to more than one x, but x cannot correspond to more than one y. So your answer is choice B. So now we'll skip down to here where it says mapping. A mapping is another way of determining if a relation is a function. In a mapping, arrows are typically drawn from the domain of a relation to its range. If no more than one arrow is drawn from any domain value to a range value, the relation is a function. Otherwise, it is not. Here are two examples. So if we look at relation A, notice how each domain value, 2 and 4, only have one arrow coming from it there. So since each domain only goes to one range, it is a function. However, with B, it is not a function because if we look from our 2, we have 3 lines, one going to 4, one going to 6, and one going to 8. So there are 3 different values for the range for that one domain of 2, so it is not a function. And also, if we look at 4, it also maps to 4 and 8, so it is not a function because we can only have one arrow coming from each domain value. So if we look at sample question number 2, it says, which relation is also a function? So we're looking for one range for each domain. So 5, there's one domain and it has 3 arrows coming off of it. So no way, doesn't work. B, 1 and 2 only have one arrow coming from it, which is good, but 0 has 2 arrows coming from it, not good. Take a look at C. If we're looking at C, even though 3 and 9 both point to the same range, each of our domains only has one arrow coming from it, so this is a function. And let's just double check with D. So D, 1 has one arrow, 3 has one arrow, 5, however, has 2 arrows, so it is not a function. So our answer is choice C. All right. Functions can also be evaluated for inputs of the domain. To evaluate a function, we substitute the function's variable with the indicated number, then find the value of the expression. So when we see f of x, right, that x is what we're going to substitute in for whatever the value that they give us here. So if we look here, it says f of x is equal to 3 plus 2 to the x. They want to find f of -1. So what we do is wherever we have an x in our original function, we're going to substitute in -1. So 3 plus 2 to the -1. And now we can just continue to evaluate it. So 3 plus, when we have 2 to the -1, that's the same as just 1 over positive 2 to the positive 1. Then if we're adding, right, 3 plus 1/2, it's going to be 3 and 1/2, which is choice C. So that's how we evaluate our function, just by substituting in the value that they wanted us to find, f of x, right, when x is equal to -1. So another thing about functions is that we can graph functions. So graphing of a function is the same as the graph of an equation, equal to y equals f of x. So when we had like y equals 2x, it's the same as f of x equals 2x when we're graphing. The domain of a function is each value's x value, or sorry, is each x value represented on the horizontal axis, and the range of the function is the y value represented on the vertical axis. So to graph a function using our calculator, ours is a little bit different than this one here. We're going to take a look at how to graph a function a little bit later on in the problem set here. So another thing here, when two functions, f and g, are graphed together on the same coordinate plane, any points of intersection are solutions to both functions. For functions f of x and g of x, the x coordinates of the points of intersections of these two functions are the solution set to the equation f of x equals g of x. So if they want to find where f of x equals g of x, we're looking for the x values where they intersect. Right? All right, so we don't care about the y values where they intersect. We're looking for the x values where they intersect. So if we continue on to the next page here, he wants to know the graph of the function f of x equals 1.5 to the x, which is an exponential function, and g of x equals 60x minus 540 are shown on the coordinate plane below. What are the approximate solutions to f of x equals g of x? So what we're looking for is where do these functions intersect? So the first place they intersect, if we're looking around, is right here. And the second place they intersect is up here. So remember that the answer to these problems here are the x values. So if we draw a line straight down from where they intersect, we see that one of them is x equals to 10. And then if we take a look at the second place where they intersect and draw a line straight down, we see that x is equal to 14. So our answers here, choice B, 10 and 14. Notice how they did put other answers, right? So like this one here looks like it crosses at about 60 on the y-axis and 300 on the y-axis, right? But remember that we're looking for the x values where these two functions intersect. So now getting into the practice problems. Some of these will be pretty quick, some will be a little bit longer. So here it says which one represents a function. So when we're given a graph like this, we want to find the function, we're doing the vertical line test. So our vertical line test, we're just drawing a straight vertical line, and if it hits more than once, not a function. So here, our vertical line hits twice, not a function. Take a look at our second one here. This one here, can draw a line here, hits 2 points. Also here, hits 2 points. So definitely not a function. We take a look here on B. On B, there is nowhere where I can draw a vertical line that it hits more than 1 point on this line. So B is going to be our function. D, however, right, we can draw a line here that goes through D, hits at 2 points, not a function. So your answer is choice B. So vertical line test, right, only hits the function once. Take a look at number 2. Number 2 says a function f is shown below. F of x equals -4 parentheses x plus 1 plus 2x. What is the value of f of 3? So to find f of 3, we're just going to substitute in 3 for x into each part of this function and solve for it. So if I write f of 3 equals -4, then parentheses, instead of x, I'm going to write 3 plus 1 plus 2 instead of x again, substitute in 3. So f of 3 equals -4 times 3 plus 1, which is 4, plus 2 times 3, which is 6. Then f of 3 equals -4 times 4, which is -16, plus 6. F of 3 equals -16 plus 6, which is -10, and it's choice A. So all we're doing here is substituting in 3 for x and then simplifying the right side of the function there. All right, moving on to number 3. Number 3 says the graphs of the functions f of x and g of x are shown on the coordinate plane below. Based on these graphs, which statement must be true? So which statement must be true? So here, if we take a look, the two functions cross here when x is equal to 4. So that means when x is equal to 4, right? So f of 4, it is the same as g of 4. So if we're taking a look, we look for which one of these matches down here, which is choice B. Now, if we take a look, f of 2, right, is going to be right here. And if we take a look at where g of 2 is, that's right here. We can see that those two y values not equal. We do the other way around. F of 2 again, right, is up here. And g of 4 is right here. Again, these two y values not equal. Then finally, f of 4, which is here, and g of 2, which is there, are not equal. So your only answer here is f of 4, which is right here, and g of 4 at the same point. That's why they're equal to each other. Number 4 here says, which relation is also a function? So remember, a function means one range from each domain, right? You can only have one range from each domain. So if you have two lines coming off of a domain, not a function. So the first one is not a function. For B, we're okay with 2 to 5, that's 1, but then 3 maps to both 6 and 8, not a function. C, 3 maps to 2 and 6 maps to 2. So this fits our one range from each domain. Even though they go to the same range, they each only have one range that maps from them. So this is our function here. And if we look at D, 2 maps to 2 different numbers, so it's not a function. So again, our choice is C, because each domain has only one range coming from it. Now I'll take a look at number 5. So number 5 says, the graph of a function is shown below. Which value is not in the domain of the function? So if we're looking here, this is not a continuous function, right? And it's not, we have some gaps here. So we have an open circle here and here, but we have a closed circle there. So if we take a look at -2, is there a y value for -2? No, because both of these are open circles. So there's actually a gap here where the domain is not, there's no y value for this x value. So this is not in the domain. So this is our answer here. If we take a look at -1, at -1, our y value is here, part of the domain of the function. At 0, our y value is here, part of the function. At 2, while we have an open circle up here, we do have a closed circle down here. So our y value is there. It's part of the domain of the function, which again only leaves us with -2 as not being a part of it. All right, let's take a look at Stella. So Stella gets on a train that is traveling directly to her state capital. She is 320 miles from this capital when she gets on the train. The train moves at a constant rate of 60 miles per hour. The function f of x equals -60x plus 320, where x cannot be, or where x is greater than or equal to 0, can be used to find the distance she the train is from Stella's state capital for any number of hours the train travels. So we have this function here. Then, as we're going through, the first part here says, what is the value of f of 2.5? So we take our original function, f of x equals negative 60x plus 320. And now we're just going to substitute in 2.5. So f of 2.5 is equal to negative 60. Then we're multiplying it by 2.5 plus 320. So when we're simplifying this out here, f of 2.5 equals negative 60 times 2.5 is negative 150 plus 320. And then finally, f of 2.5 is equal to, this here equals 170. Now it wants to know what is the meaning of f of 2.5. And if we're taking a look here, what we're saying is f of 2.5 is the hours that Stella is on the train. And then our y value here, this 170, is the distance that she is from the state capital. So what does f of 2.5 mean? It means that after 2.5 hours, Stella is 170 miles from the capital. So our x values represent the number of hours on the train, then the y value that we find, the range, right, will show us how far away we are from the capital. All right, let's keep going along here. The last question, question number 7, it has to do with graphing the function here. So it says that the functions f of x and g of x are shown below. Graph these functions on the coordinate plane below for all the domain values of x from 0 to 5. So we're going to have a table, right? And I kind of set up the table already, but we want the table to have x values from 0 to 5. And then we want our y values, right, to be made up of the y values from these functions here. So what I'm going to do is flip over to our calculator. And let's take a look. So on our calculator, if we add a graph page, if we want to put these functions in there, right, we just place them right in. So 3 to the x, and then we'd hit enter. Then if we want to graph another function, right, we'll hit tab and put in our second function g of x, which is 9x, enter. Now remember, to get our tables, we're going to hit tab, and then we want to hit the letter T for table. Or sorry, actually, I lied to you there. So in order to get our table, we hit Control T, and then we'll see our table for our functions here. So what I'm going to do is kind of, let's see if we can see both of these at the same time. So what we do here is on our chart that we have here, right, we'll fill out the different values for each of these. So when x is 0, f of x equal to 3x is equal to 1. So we'd write in a 1 here, and then continue down to fill in the rest of this table all the way down to 243. Then we do the same for g of x. So g of x, which is this column here, is equal to 9x. So at 0, g of x is 0. At 1, g of x is 9, 18, 27, and so on all the way to 45. So we can use this table. Then you can kind of complete this table over here. Then I'll remove this. And this is what we have in our calculator. So when we're looking at this, in order to put this onto our graph, right, we have x values, and then each of these are its own y. So maybe this is y1 and y2. So first, let me actually change the color on my second one here. Second one will graph in red. So for the first one, we have to see our x values are only going up to 5. So what we're going to do is spread this out a little bit, and every 2 boxes will count by 1. So 1, 2, 3, 4, and 5. Now our y values have to go all the way up to 243. So I know that we have 10 boxes here. So if I count from 0 and we go all the way up to 250, then we'll fit on here. So if I know I have 10 boxes and I want the highest point to be 250, each box is going to be worth 25. Now when I'm labeling here, it's a lot of writing if I labeled 25 for each one. So I'm going to skip and count by 50s. So 50, then skip 100, skip 150, skip 200, and then the last one, 250. So I'm going to start by graphing our first function, right, which is going to be in black, and it's f of 3 to the x, which is an exponential function. So at 0, we really are kind of at a point 1, which is pretty close to 0 down there. At 1, we're at 3, still pretty small, because remember, this line here represents 25. At 2, I'm at 9, so I'm a little bit closer to maybe halfway up there. But then at 3, I'm at 27. So now I'm right above 25. At 4, I'm all the way up at 81. So remember, we have 50, 75, then 81 will be a little bit above that. And then at 5, I'm at 243, which is almost all the way up to 250. So we'll put a point up there. Now I'm going to connect these with as smooth as curve as possible to show my exponential function there, and then we'll label it f of x equals 3 to the x. So now I'm going to graph our second function, which is g of x is equal to 9x. So at 0, here we'll point at 0. At 1, we're up to 9, which remember was the same as when we were at 2, so it's about right here. Then at 2, we get up to 18, which is still below 25. At 3, we're at 27, which is the same point as here. 4 is up to 36. And then 5 is 45. Then for this one here, it's a linear function, so I'm going to do my best to draw a line here. All right, so this line's a little bit higher than it should be. Let's see if we can bring it down a little bit. All right, so this is our function here. Now if we're labeling it, this is g of x is equal to 9x. So these are two graphs, just graphing those tables onto here. Use the graph from part A to approximate the solution of f of x equal to g of x. Well, we have our table here, so we can see when f of x is equal to g of x, but we can also see on our graph that that is where they cross. So f of x is equal to g of x when x is equal to, we look here, 3. All right, so that is the end for this lesson here. So keep going through. Remember, this week is going to be lessons 1, 2, 3, and 4. They'll all be posted by Thursday, and then we'll post the quiz up there on Friday for you to fill in your answers to these multiple choice questions in each lesson. All right. If you have questions, make sure to reach out. Other than that, thank you for watching.